Globally, there are about 60,000 ships operating, of which 3,500 vessels are participating in our program.
So I think the results is already good for the applications, and also they have already met the customers' expectations.
So it sounds like when compared to the traditional manufacturing techniques, 3D printing is up there in terms of the equivalency.
Being in the aviation industry, the favorite part of my job is to be able to see various cabin settings and innovative products. The estimated lead time for this is 2 weeks. We should start and get the production ready by end of next week.
Nothing is ever the same. Coming into this role, I am basically the head of the tech center, looking at additive manufacturing specifically. Traditionally, for a lot of the parts that we see in the industrial sector, especially in maritime, these parts are mass-produced. In the spare parts business, you don't actually purchase in bulk. You're looking at a part breaking down, you want to get just one part to replace that. With 3D printing, what happens is that when the demand arises, the order is placed to us, and at that point, we then begin the manufacturing process. So it's very efficient, and that we're doing this at a point where we are delivering and producing closest to the point of need. When we do that, we're also saving the environment, and we are using resources more efficiently. We're not shipping things around the world. It's a new way of which we are approaching fabrication. We actually do a lot of couplings. Essentially, they're like giant shock absorbers. So these are typically used on offshore platforms, also in ships. And we can make them very quickly in different sizes. The propeller that we have over here is actually printed by one of our larger systems. There's a partner that we have that specializes in bronze additive manufacturing. We're also able to make small gears that are from obsolete systems that may be no longer being supported. So essentially, we are able to fabricate rubber-like substances all the way through to plastics, through metals.
I work in the aviation industry, and I lead a team of personnel that manufactures cabin interior parts utilizing additive manufacturing. Being in the aviation industry, the favorite part of my job is to be able to see various cabin settings and innovative products. As we all know, there is a great emphasis on cabin ergonomics and even innovative designs. In cabin parts demand, the lead time for some of the parts can go up to 3 to 6 months for the parts to arrive. Whereas utilizing 3D printing technology for identification, redesign and manufacturing, the parts can be available within 2 weeks to a month.
This is a bumper strip end cover. It is normally located around the galleys, the walls of the aircraft cabin, and it prevents from the trolleys to hit the walls. This end cap breaks quite often actually, which means there's room for improvement. So compared to the original solution, you can see already how much stronger the component has been produced, and this prevents the part from breaking too often, which brings down the repair costs of the airline as well. This is a seat back shelf of an aircraft, and you see damages on the component. One of these parts easily can cost $1,000 and need to be replaced quite frequently. We create components which we will actually glue or put inside the seat and stabilize this particular area. First of all, the part will not crack anymore at this location. And second of all, you reduce tremendously the amount of material used by replacing this kind of components. Everything costs you maybe only $250 to $300.
So the part is actually made of metal, fitted in the vessel's ventilation exhaust system. So it is highly corrosive.
So this is a good example of how we can change the material to enhance the performance and lifespan.
What's the initial feedback from the engineering team in terms of doing a material conversion and still maintain the performance of the part?
Just to put some figures to this, globally there are about 60,000 ships operating, of which 3,500 vessels are participating in our program.
Do you know what's the lead time that they're expecting?
Yeah, so they require the part in 5 days to be delivered in Singapore.
Wow, that's tight.
The ship might be pulling into a port in Asia, and then there's a part in a system that is not working. By giving us that notice, we are able to then plan out the engineering and fabrication of this part for a supplier that is closest to that particular port. When parts reach this age, and which in this particular case is more than 20 years, the inevitable choice is to replace out the entire system. And so when you can think about doing that, it's a bit like hacking out your entire bathroom just to actually change out the tap. So with 3D printing, we're able to remove this particular situation and really surgically target the part that is no longer working.
Over here you can see some of the corrosion problems that currently happening.
I guess if we use aluminium in sea conditions, then you can expect this kind of...
Yes, that's true.
So basically we grow it as one piece with carbon fiber and then see whether through simulation we can get the same results. Yeah, that sounds good.
Some time to set up a simulation.
Can.
What I'm doing here is the cabin walk, which we typically conduct to identify parts that can be manufactured using additive manufacturing. So the criteria that these are basically parts which are in high contact points with passengers. One of the areas that we commonly look at is the seat armrest. So what we typically do is we evaluate the part and we look at whether the common areas that are damaged can be reinforced or improved in design. So thereafter, we actually print a prototype for trial, fit and test to evaluate the effectiveness of the improved design solution. Another area that we look at is on the seat shroud itself and also the consoles around the seat shroud. The scanning is an integral part of the whole additive manufacturing process, where the part is being scanned to get a quick model. This will enable us to redesign the part and actually reinforce and improve the design. Based on this, we are then able to manufacture a prototype to be fitted for testing. The soap holder is one of the parts that we identified in the lavatory, which is required to hold the soap container in a fixed position.
The only concern is how they are going to actually install the soap holder part, because they need to drill 2 M6 holes on the back to be attached to the wall.
I think this is actually quite a straightforward part. We can actually print 12 pieces in a batch, and printing time will be about 6 hours.
Once the part is being identified on the aircraft, we optimize the design. We print the part at the lowest possible cost with the highest quality. After this improved design is incorporated, the parts are being sent for production. The estimated lead time for this is 2 weeks. So to provide with some buffer, we should start and get the production ready by end of next week.
This is our warehouse where we keep our certified material. It is very important to maintain a very accurate temperature as well as humidity level. The raw material will absorb moisture, and we need to prevent the moisture of getting into the material because it will increase the filament size actually and could probably lead to a failure in the print. Basically, after finishing the design, we will load a digital file into our machine and send it for printing.
In additive flight solutions, we focus on polymer, which is plastics for 3D printing. So in the field of metal additive manufacturing, the OEMs are actually already incorporating the technologies for aircraft, even engine parts. So the number of structural parts and engine parts utilizing additive manufacturing will actually increase tremendously as the OEMs have actually scoped in which are the parts that they intend to produce using this technology.
We have seen breakthroughs in computing power that allows for the digital design of this file to be done very, very efficiently, very quickly. The fabrication technologies of these printers also improving on a year-by-year basis, and nowadays, literally in hours, you can print out an industrial strength part. So the technology is still evolving, but we are now at a point in time and space where the confluence of what is possible and what the customer expects are starting to align. I do not need to have these parts be stored in different warehouses around the world. I don't have to pay for the rental of these warehouses. I'm also able to basically make improvements on the fly to these parts, something that, again, the traditional process of which these spare parts are being fabricated will not be able to offer. With any new technologies, there are upsides as well as potential pitfalls in which we have to be aware of. One thing that is of concern would be the securing of the digital information.
So in 3D printing, there's a lot of data being transacted between us and our fabrication partners. These include design files to engineering drawings that illustrate the post-processing requirements, for example. So all these data form very important intellectual property that must be protected within our venture and with our manufacturing partners as well. So with this in mind, we have actually conducted several activities to ensure that we have a cyber-secure infrastructure.
Our main challenge was to optimize the process for this specific build. Basically to take into account the angles of the part.
Alex from Optimac is a technical individual that contributes a lot in terms of his knowledge over the last few years that he has been in the arena of 3D printing.
We've started working with ThyssenKrupp towards the end of 2020, identifying applicable parts for the maritime industry, parts that can be used as end-use parts on ships. Here we utilized our 5-axis capability, so we've managed to create this kind of curvature and the hollow structure. Casting requires you to prepare a mold. Molds are very expensive. So we have shown savings of up to 80% with certain parts.
So I think for now we will send off your sample for testing, and then we would like to add some...
The part that Alex's team is working on has not been tried before. So in this aspect, we are running into the unknown. We're on the cusp of innovation sort of explosion. We are in the age of electric vehicles, we're in the age of drones being flown, that eventually these items would also have parts in there that are additively manufactured. I cannot help but think about what this means for other industries in the future, during my kids' generation. It's very smooth, very sweet herb.
DNV is one of the world's foremost certification bodies as it pertains to maritime industries. They are the ones that write the rules in terms of how parts are being fabricated, how these parts should be tested, as well as installed on board ships.
So we're going to test the current component. We're going to pull it to a certain extent where it will snap, and then we will know how much strength these parts can withstand up to. We are also going to do other tests such as impact tests, where we're going to knock a ball onto the parts to check the material and to ensure that the parts are being formed correctly.
If we are confident with the good quality of additive manufacturing, we will issue the relevant certificate for the final products.
Yeah, this is something that our customers are asking for. We need the classifications, society's approval.
I guess that's the same case for any new technology, where initially people have less trust or less confidence to use the new technology. Then we do a lot of testing, then we can issue a certificate if we are confident. And then later the industry will have the trust to utilize the new technology to replace the existing ones.
I would say the pandemic has very hard affected the whole aviation industry. Not only airlines, but of course also parts suppliers like us. Most of the aircraft have been grounded the last 2.5 years, and therefore the demand of spare parts or cabin replacement parts have been minimized a lot. We are now going to the customer side. We want to present our design findings and show the first test piece and discuss alterations in the design concept.
So we did some simulation on the loading. Here you can see the stress distribution.
Are we assuming there's actually this one-directional pulling force onto the ring of this component?
We printed out a sample part actually, and you see already from the holding of the component how we increase the strength of the element, increase the material over here. So even in case you are hitting the frame with a bottle loading, it will not crack.
We put it on a fixture, and here is the complete scan of this part.
Can you just show me the back of the part?
Yeah, you can also flip this,
okay.
And it's a first scan.
After having the part produced on our 3D printing machines, we take the part to our quality inspection here, and we use an optical scanning measuring machine with a 35 microns accuracy. And one further advantage actually is that we have the scan data available even after we deliver the component. So at any time when the customer or the aviation authority is asking for some data verification, we have all the measuring data of each and every component available at any time.
We actually did a design iteration and changed a bit of the radial dimensions. So this improved the ability to withstand the load by another 1.5 times. So this is now much more stronger.
I had to go to the bathroom.
Okay, well. This afternoon we're meeting our client who's going to be coming to share with us on the recent part that we have delivered. The part that the client ordered is a cooling fan impeller. It is a part that is typically fabricated in metal, hence subject to high levels of corrosion when used on board maritime vessels.
Since this was a new implementation of the part, we actually changed it from aluminium material over to composite.
I also like the idea of copper being replaced by plastic. We're looking at a 22-year-old gas vessel. Their exhaust fan has broken down, and all our sourcing efforts were in vain. So then we reached out and eventually designed that thing together with you in our training to the guys on board and on shore, that if you have a part that has a delivery time of more than 3 or 4 months or is an obsolete part, so that means in standard spare part terms no longer available, that is a perfect candidate for printing.
Once the parts are put into the field, we actually expect no less of these parts as compared to their normal conventional cousins. These parts are expected to work for upwards of years, sometimes even decades.
The biggest challenges actually is still acceptance of additive manufacturing. I believe the future of additive manufacturing will come first of all with new generations of machines which are faster and can produce more economical price components. Establishing a moon colony, for example, you will be able to reproduce in any material replacement part, repair parts on demand what you need actually.